The question continues by asking how much energy it takes, how much the internal energy of the gas changes, how much work is done, and so forth. Okay? Now, somebody quoted this formula here. I don't want to talk about that formula right now, but I want you to think about that formula. I want you to think about what's going on so that we can understand what the formula means and what it's telling us. Okay, so what do we know? We know that pressure goes from 100 kilopascals in stage 0 to 110 in state 1. Volume goes from half a liter to half a liter, no change. Temperature goes from 300 Kelvin to 330 Kelvin. Okay, so now I'll go ahead and use the symbol. Delta U 01, your text uses delta U for what? The change in internal energy. What is delta U from 0 to 1? It's something you can calculate using a formula without understanding what it is, but in terms of everything we've done so far, we're thinking in terms of the kinetic energy of the molecules in the system. And the change in delta U is the change in the internal energy. That is the change in the kinetic energy of the molecules. So what do we know about the change in the kinetic energy of molecules? Well, we know that the change in the kinetic energy of the molecules, the total kinetic energy of the molecules in the gas per mole, is 1/2 R delta T for each degree of freedom. Now, I'm not going to go back over an explanation of that. We covered that pretty extensively. We should understand how that relates to the kinetic theory, to the development, to the impulse momentum of a molecule bouncing off of a wall, etc. Well, now, since air is diatomic, that means we have 5 degrees of freedom, 3 translational, X, Y, Z, and 2 rotational. Whatever the orientation of the molecule at the given instant, there's an axis perpendicular to the axis connecting the diatomic atoms in this direction. Then there's another axis perpendicular to that that's also perpendicular to this direction. And maybe instead of gesturing, pretend that the molecule is at the 2 ends of this thing, which is dark and doesn't contrast. So I'll just use a piece of chalk. Okay. Now, say we got 2 atoms attached to the ends of this piece of chalk. We have an axis perpendicular to this axis about which this system can rotate. And we have another axis perpendicular here to the first axis and to the axis of the molecule. And those 2 axes are the independent directions in which, the independent axes about which the atom or the molecule can rotate with kinetic energy. So we have 2 of those. So we have 3 translational, 2 rotational, a total of 5 degrees of freedom. 5 times 1/2, of course, is 5/2. And we also know delta T. Delta T is the 30 degrees Kelvin, or the 30 kelvins. So all we need is to find the number of moles, because, of course, this is the change per mole. Now, this 5/2 R is what you call CP, or CV, I'm sorry, in a formula for the internal energy U, but we want to reason it out to understand what that formula tells us. We'll get the formula at the end. Okay, so we know delta T, we need the number of moles. We've calculated the number of moles in 500 liters, 500 milliliters at 300 Kelvin, 100 kilopascal, a number of times. Here it is again. We get about 0.02 moles. Now it's a little more than that. It's not completely accurate. It's more like 0.23 or 24, I think. But now our change in internal energy then is the number of moles, 0.02 moles, multiplied by 5/2 R, which is approximately 21 joules per mole Kelvin, multiplied by our change in temperature, the 30 Kelvin, and that comes out to 13 joules. Now, what have we done in terms of symbols? This is the delta U 01. So we have delta U here. This is N, the number of moles. This is CV, the 21 joules per mole Kelvin, which we reasoned out based on kinetic theory and degrees of freedom. And of course, there's our delta T. So we have delta U equals NCV delta T. This should not be the beginning of your understanding. The beginning of your understanding should be the kinetic theory and how this is built up, so that the formula expresses something that you already understand. Now there's another alternative. Let's take the formula and work it backwards and see what everything in the formula understands and where it comes from. That's equally valid, and if that's the style you prefer, just make sure you've done that so that you deeply understand what this formula is telling you and can visualize what the formula is telling you in terms of the behavior of the particles in the gas.